Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Peter has been working in various areas involving machine learning for a number of years, and most recently he's been working on natural language processing applications of machine translation technology with a focus on lexical relationships and lexical similarity, including similarity. And today he's going to be talking to us about some work he's been doing on SAT analogy questions and using a model of lexical relatedness called Latent Relational Analysis to try to solve these SAT analogy questions, and he's got some really interesting results. Thanks.
Thank you. Hi. So I'm going to talk about how a computer can pass the SAT, at least a very small part of it, the part dealing with analogy questions. First, I'll talk about what the problem is and applications for a measure of relational similarity, which is what you need to solve these kinds of SAT questions. Related work, my algorithm, which I call Latent Relational Analysis, and two groups of experiments. The first group is word analogy questions taken from the Scholastic Aptitude Test, and the second group is a problem of classifying relationships in noun-modifier phrases. And I'll end with a discussion of the results. So if you have a question while I'm talking, feel free to ask me, and if I'll be answering it later, I'll tell you that. But otherwise, I'll try and give you an answer. So there are at least two kinds of similarity, of semantic similarity: attributional similarity and relational similarity. Attributional similarity is basically synonymy. It's a degree to which two words are semantically similar. And here's some examples taken from the test of English as a foreign language. In the test of English as a foreign language, they have multiple choice questions with a sample word, and then there's 4 choices for the most related word. And these are the kinds of solutions that you'll see in the test. Levied is synonymous with impose. Zenith is synonymous with pinnacle. So there's been a fair bit of work on using statistical techniques to measure attributional similarity of words. What I'm interested in, or at least what I'm going to talk about today, is using statistical techniques to measure relational similarity. And here we need a pair of words, and we're interested in the relationship between the pair. When a pair of words has, when two pairs of words have a high degree of relational similarity, we say they're analogous. So mason is to stone as carpenter is to wood. The relation between mason and stone is similar to the relation between carpenter and wood. A mason is an artisan who works with stone. A carpenter is an artisan who works with wood. And these examples are both from the Scholastic Aptitude Test. Traffic is to street as water is to riverbed. So if you had a good measure of attributional similarity, what could you do with it? Well, I think there's a lot of things that you could do with attributional similarity. There are many applications that have already been described in the literature. Recognizing synonyms, information retrieval, semantic orientation. Semantic orientation is whether a word is positive or negative. Like the word honest is a positive word. The word criminal is a negative word. You can tell the orientation of a word if you have a measure of attributional similarity. Grading student essays, measuring textual cohesion, Thesaurus generation, word sense disambiguation. There's lots of things you can do with a measure of attributional similarity. What can you do with a measure of relational similarity? Well, this is a bit speculative because it's only recently that we've been able to measure relational similarity, but I think it also has lots of potential applications. Of course, to prove this, we need to actually demonstrate that it can do these things, but I think it has potential value for word analogies, semantic relations, machine translation, word sense disambiguation. There's lots of possibilities. Basically, anything that you would use attributional similarity for, you'd probably also find some value in using relational similarity as well, or perhaps instead, depending what you're trying to do. So the approach that I'm taking to measuring relational similarity is a corpus-based approach, unsupervised learning. And the work I'm going to talk about today is based on some earlier work I did with Michael Littman, where we use a vector space model for measuring relational similarity. And I'll describe in a bit more detail what the vector space model is in the context of measuring relational similarity. But we build on that work, and I call it Latent Relational Analysis, and it borrows ideas from both the vector space model and from Latent Semantic Analysis. So here's an example of a question from the Scholastic Aptitude Test. There's a word pair that's called the stem pair, Mason-Stone, and then there are 5 choices, 5 word pairs, and you've got to choose the one that's most similar to the stem pair. And basically the way you answer this kind of question is you look at each of these pairs and try and figure out what the relationship is. And here I've just sort of manually added in what I think the relationship is in each of these pairs. And once you've labeled the pairs according to their relationship, you can see right away that the correct answer for this question is B. Mason is to stone as carpenter is to wood. They have the same relationship. Mason builds with stone, carpenter builds with wood. So one thing you can do if you can recognize similarity in semantic relations is you can answer SAT questions, but there are many other potential applications. Noun-modifier relations are one of them. In noun-modifier relations, you have a pair of words like sleeping dog, where there's a head noun dog and a modifier sleeping, and the relationship isn't stated anywhere. You're just given the phrase sleeping dog, and somehow you figure out what the relationship is. So in this case, it's in a state of, the dog is in a state of sleeping. But in sleeping pill, it's the pill causes sleep. And sleeping area, it's an area for sleeping. Each of these, there's a different relationship. Even though they all have the modifier sleeping, there's a different relationship in all of these pairs. And there's no obvious way to figure out what that relationship is. But there are lots of applications that would benefit if we could get a computer to figure out what these relationships are. So if we had an algorithm that could solve SAT analogies, we could use it to figure out noun-modifier relations. And the idea is just to wrap a nearest neighbor learning algorithm around the similarity measure. So you have a training set where there's a bunch of noun-modifier pairs that have been manually labeled into various classes, and you're given a new noun-modifier pair and asked to guess what the label is. You just go through all of the training cases, measuring their relational similarity to the new case, and the one that has the highest relational similarity in the training data, you look at the label that was manually assigned to it, and you guess that that label applies to the new case. So noun modifier pairs are very common. I wrote a little script that went through WordNet 2, and looked for all the noun modifier pairs that were in it, and there was more than 26,000 just in WordNet. And if you say parse text from the web and look for noun modifier pairs, my guess is you'd easily find hundreds of thousands in English, perhaps millions. So they're extremely common, and that means it's important for us to be able to handle them with our computer software. If we could classify noun modifier pairs properly, I think that would be useful, for example, in machine translation. Suppose you had to translate the noun modifier pair electron microscope into another language. Well, if you're lucky and you're dealing with a pair of languages like English and French, you can probably just look it up in a dictionary and see right away, electron microscope is translated as such and such in French. But if you have a more obscure pair of languages, you're not going to find it in a dictionary, and you'd have to break down the component words and translate the individual words and then reassemble them in the target language. And there it would be very important to know the relationship. It would determine how you would translate the individual words and also how you would reassemble them. So in an electron microscope, the electrons are an instrument used by the microscope for seeing objects. They're not, it's not a purpose relationship, it's not a material relationship, it's not a microscope built out of electrons. And knowing that could be very helpful. The same kind of argument applies to information extraction and word sense disambiguation. This relational information can be very helpful. So the most closely related work is the work I did recently with Michael Littman using the vector space model. The basic idea is we're given a pair of words A, B, another pair C, D. There's some hidden relationship that we don't know, and we want to uncover these hidden relationships and then measure their similarity. So the approach we take basically gets its inspiration from information retrieval, where in information retrieval you have a query and a set of documents, and you want to measure the similarity between the query and each of the documents in the set, and then you take your documents and sort them in order of similarity, and that's the hit list you get back from a search engine. It's essentially similarity-based ranking. And the typical way to measure similarity in information retrieval is to take the cosine of the vectors. So you represent the query with a vector, you represent all of the documents with vectors, and you just calculate cosines and sort all the documents by their cosines. So we're using the same idea here, except that these vectors represent relationships instead of representing documents and queries. Now here's the formula for calculating the cosine between two vectors. And for someone who knows how the cosine is calculated, you'll probably just look at the formula and say, yeah, I know that. But if you don't know, probably the formula isn't helping. So here's a little picture. You have two vectors here. They're the red lines. And you want to calculate their cosine. Well, first of all, you have to normalize the vectors so that they're the same length. Because the length of these vectors just depends on the frequency of the words. And we don't really care about the frequency. It may vary for rare words and more common words. So we make the vectors the same length. We normalize them to unit length. And that's what the blue circle is. It's a circle of radius 1. And where it intersects the red lines, you get the red lines have been normalized to a length of 1. And then the cosine is just a projection of one line onto the other. So you take one of those blue points and project it onto the line, and it doesn't matter which one you do, you'll get the same result. And there you can see the cosine in green. If you make the angle bigger, the cosine goes down, and if you make the angle smaller, the cosine goes up. So the cosine will be -1 when the angle is 180 degrees, and it'll be +1 when the angle is 0 degrees. It's basically a very simple idea.
Are you just saying how you go from two words to a vector representing a relationship?
I'm going to say that right now. So we're given a pair of words, and we want to make a vector out of them. Well, what we do is we have a bunch of joining terms, and we actually have a list of. This is not the current work I'm describing. This is the work that I did earlier with Michael Littman. We had a fixed list of 64 joining terms, and they were terms like with, to, for, and we take the word pair like mason, stone, and we join it together to make a phrase like mason with stone, stone with mason. And then we just do a search on a search engine. We chose Alta Vista. So we search as a quoted phrase, so we require an exact phrase match on the phrase, say, mason with stone, and we just look at how many hits we get. We ignore the exact documents. All we care about is how many documents contain Mason with stone, how many contain stone with Mason. And so from 64 adjoining terms, we get 128 queries because we do them in both order, Mason with stone and stone with Mason. And the 128 queries give us 128 numbers, the hit count for each of those phrases. So
are they all prepositions, or did you use any verbs?
there were some verbs. They're sort of a mix of prepositions and verbs, and I won't say much about that because that's the past work. And one thing we didn't like is this list of 64 terms was just kind of hand generated and rather arbitrary, and we didn't have time to optimize it because one run took so long that trying to find the optimal list of joining terms would have been just infeasible. And in the latest algorithm, we don't have a fixed list anymore. So here's an example. Again, traffic, street, and water riverbed. The vectors would have 128 elements. In this example, I've just chosen 5 elements out of that vector. So traffic in the street gets 615 hits on Alta Vista. Water in the riverbed gets 91 hits. If you look at these two columns, the column for traffic street and the column for water riverbed, you see they have the same general pattern to them. And that's what I'm trying to show with the little red histogram on the right-hand side. The pattern is lots of hits, a few hits, lots of hits, lots of hits, a few hits. And if you look at the total line, there are many more hits for traffic street than water riverbed. There are a lot more documents on the web, in other words, that talk about traffic and street than that talk about water and riverbed. And this comes back to why we want to normalize the vectors, because the vector for traffic street will be a lot longer than the vector for water riverbed. So we have to normalize them to correct for that. And once you've normalized their lengths, you can see much more clearly that they have the same pattern to them. And here's a SAT question that this was taken from, and you can see the cosines for each of the 5 choices, and the one that maximizes the cosine is the correct answer for this SAT question. So that was past work. That's the work I did before with Michael Littman, and now I'm going to describe how I built on that to improve the performance a bit. So there's 3 main things that I've added that distinguish this from the vector space model. One is we no longer have a fixed list of joining terms. Instead of having a fixed list of 64 joining terms, we look at the data itself, the corpus, and build a list dynamically from the data. Another is using the singular value decomposition, which is something that they do in information retrieval for measuring attributional similarity. Here I'm using it for measuring relational similarity. And the third thing that is new is the use of synonyms. So the idea here is, given a word pair like Mason stone, I don't just use Mason and stone. I look for synonyms for Mason and synonyms for stone to try and gather more data so I have more reliable vectors. So I'm going to take you through the steps of this algorithm, and I'll use this SAT question as an example of what I'm doing in each of these steps. So the stem is court volume, and there are 5 choices, and the best choice here is mile distance. So court is to volume as mile is to distance. So the first step is to look for synonyms that we can substitute in. And in this step, I'm using Dikang Lin's automatically generated thesaurus, mainly because his thesaurus gives you a similarity score for each of the words. So I can score all of the words according to their similarity and take the top ones. What I do is I take the top 10. So given the word pair court volume, I take the top 10 most similar words for court and substitute them in. So I have pint volume, gallon volume, liter volume, and similarly the top 10 for volume. Now, you'll notice here that in this context, the replacements I have for court are reasonable replacements, but the replacements I have for volume are using a different sense of volume. The sense of volume as the amount of money that's being exchanged on the stock market or something like that. So court turnover, court export, these aren't right. So the next step is to do some filtering. And the way we filter these is just do a search in our corpus. And here we're using a terabyte of text that we got from the University of Waterloo. They crawled the web with a web crawler and gathered a terabyte of text, and they have a custom search engine for that terabyte. So I just search for quart near volume and see how many hits I get, gallon near volume. And in the previous step I had 20 alternatives to the original pair, quart volume. What I take is the top 3 alternatives that have the highest frequency. I'm just going to back up to step 1. So quart export. Just if I look in the corpus, the terabyte of text, quart and export very rarely appear together. So if I just drop out the least frequent pairs, I get higher quality alternatives. Now the third step is to find phrases that contain the 2 terms of interest. So given the pair quart volume, I search in the corpus for all phrases that contain quart and volume within a certain window, a window of 5 words. So I have things like quarts of volume, quart total volume, volume in quarts. Now the fourth step is to build patterns dynamically, and instead of having a fixed list of joining phrases, here I'm building the joining patterns from all of the phrases that I found. So if I found a phrase like volume being about 2 quarts, the patterns would be generated by replacing the intervening words with a wildcard. So being about 2 would be one pattern, wildcard about 2 would be another pattern. So with 3 intervening words, there's 8 possible patterns, and a single pair like volume and quart may have 1,000, 10,000 phrases in the corpus, and once I look for all these patterns with wildcards, I quickly get into tens of thousands of patterns, and that's just for one pair of words. With the whole collection, the whole SAT, the whole collection of questions from the SAT, I have 374 SAT questions. Very quickly, there's millions and millions of patterns, and so I need to somehow reduce that. What I do is I just count the frequency of the patterns in the corpus and take the top 4,000 most common patterns. Now the next step is to build a matrix so that I can do the singular value decomposition. That's the same idea as what they do in latent semantic analysis. And in this matrix, the rows will correspond to word pairs and the columns will correspond to patterns. So first of all, for the rows, the only slightly tricky thing here is given a pair like quart and volume, I use a pair in both directions. So I have 2 rows for that. One row for the quart volume direction and another row for the volume quart direction. And this enforces a kind of symmetry on the matrix. And the idea is that we know that there's a symmetry in relations. So if I have an analogy such as A is to B as C is to D, it also follows that B is to A as D is to C. As background knowledge, we know this about analogies, and I can use that symmetry in the matrix to kind of guide the singular value decomposition. And again, when I'm building the columns in the matrix, I enforce a kind of a symmetry too. So I have 4,000 patterns, but I get 8,000 columns because I use the patterns in both directions. So now I know what my rows are, what my columns are. I fill in the matrix by counting the frequency of these phrases with the wildcards in them. So how do I figure out what goes in cell IJ, the cell that's in row I and column J? Well, I know what pair is the row, it's court volume. I know what the pattern is for the jth column. It's word 2 of wildcard word 1. And I can just search in the corpus, see how many hits I get. In this case, there's two matching phrases, so the value 2 goes into the matrix. Now I just apply some standard stuff from the latent semantic analysis. First, calculate the entropy of the matrix. The idea here is entropy gives more weight to the patterns that vary a lot. So if you look down a column in the matrix, which is one pattern, if the values in that column are pretty much the same all the way down the column, then that tells you that this pattern isn't very useful because it's not distinguishing the rows. But if you see a lot of variation as you look down the column, some high frequency places and some low frequency places, then this pattern is doing something useful. It's distinguishing the rows. So you give more weight to the columns that are better at distinguishing the rows. Apply the singular value decomposition, and I won't go into what that is, but basically you can just think of it a way as smoothing the matrix. There's bound to be some noise. It just kind of smooths the noise out for you. We're getting to the end here. There's just 2 more steps. So step 11, you've got a pair of 2 pairs of words you want to compare, A, B, and C, D. In our example, you want to compare court volume and mile distance. Well, first of all, you look up all of the alternatives. From step 2, we had 3 alternatives for court volume and 3 alternatives for mile distance. So including the original, we have 4 choices for each of them. That gives us 16 combinations. We measure the cosine for all 16 of those. So for court volume, we look up the row in the matrix. For mile distance, we look up the row in the matrix. We now have 2 row vectors. We calculate the cosine of the row vector, and in this case it's 0.5. So we now have 16 cosines. Step 12, we do some more filtering here. If any of these cosines are lower than the cosine for the original pair, they get dropped out. So court volume, mile distance, that's the original pair that we started, the original pair of pairs that we started with. Court volume, feet distance isn't as good. It has a lower cosine. And pumping volume, it's a good thing that drops out because pumping doesn't seem to be the same word as court, so it's just noise that was introduced when we were using the Thesaurus in the first step, but it gets dropped out now because the cosine is low. So once we've dropped out the lower cosines, then the final answer is just the average of all of the cosines that are left. And it turns out that gives the correct answer for this particular SAT question. So I tried the highest and it doesn't work as well. Averaging them gives you some noise resistance that taking the maximum doesn't. So these are the 12 steps of the algorithm. Lin's thesaurus, decaying Lin's thesaurus comes in the first step when we're looking for alternatives. The Waterloo multi-text system comes in when we're searching for phrases that contain the pairs of words. And I use Doug Rhodes' Singular Value Decomposition software. So that's the algorithm, and now I'll talk about the experiments. As I said, there's 2 sets of experiments. The first set is with word analogy questions. So Michael Littman gathered 374 SAT questions, and that's what I've been using for these experiments. And I'll just mention as an interesting aside that SATs this year will be dropping the analogy questions. So there's apparently some resistance to the analogy questions. People felt that they were too difficult. So what we do here is calculate, using relational analysis, the relational similarity between the stem pair in each of the choices, and the guess is the answer that has the highest relational similarity. Some questions have to be skipped because their row vector, if you look into the matrix, is a 0 vector, and you can't calculate the cosine, or the cosine is 0, or basically all of the questions get the same score, so there's no way of picking out one of them as being the answer. So these are the results. This is comparing 3 different algorithms. VSM-AV is a vector space model, the work I did with Michael Littman, using AltaVista as a corpus. Now I'm not using AltaVista anymore. Instead, I'm using the Waterloo multi-text system. So to make the comparison fair, I've replicated the vector space model results with the Waterloo multi-text system, and then I have the most recent results with the Latent Relational Analysis. So one thing to point out is that Latent Relational Analysis gets 56.4% correct on the SAT test, and the average college-bound senior high school student gets 57%. So within statistical noise, this algorithm is doing as well as the average student is. Another interesting thing to point out is when I switch from the AltaVista corpus with the vector space model to the Waterloo corpus with the vector space model, the number of skipped questions goes up from 5 to 34. That's because a lot of the corpus, the Waterloo corpus, is a lot smaller than the AltaVista corpus by a factor of about 10. So a lot of the word pairs just don't appear together. So if you search for Mason Stone, for example, there might not be any phrases in the Waterloo corpus that have both Mason and Stone. And this, the drop from VSM-AV in the score, 47% for VSM-AV to 40% for VSM Waterloo multi-text system, that drop is largely because of these missing words that just don't appear together in the corpus. But interestingly, with the latent relational analysis, the number of questions skipped is comparable to what I'm getting with AltaVista, even though it's a much smaller corpus. And that's because of the synonyms that I'm using. So that was a motivation for introducing those synonyms. It was to deal with the sparsity of the data in the corpus. So the second batch of experiments, these are applying this latent relational, yes?
Did you do any, I mean, so there's a whole bunch of parts of your system. So for instance, let's take you don't mind taking questions now, do you?
No, but I can guess what you're going to say. You're going to talk about ablation studies.
Yes.
I don't discuss those here, but I did ablation studies, and basically all the parts are doing something useful.
Okay.
But I don't have any...
Which are the most important parts?
The single most important... I think there's 3 important parts. Compared to the vector space model, the single most important part is that I'm not using a fixed list of joining terms anymore. Instead, I'm dynamically getting the joining terms from the data. Instead of having 64 joining terms, I now have 4,000 patterns. And that's responsible for a huge improvement. The other 2 things are the use of synonyms, Deking Lin's Thesaurus, and the use of the singular value decomposition. Those are roughly equal in terms of how much of a gain they give me.
You don't remember offhand how large that gain is?
It's discussed in the technical report, but I don't remember the exact numbers.
Yeah.
Just for calibration, do you know what the baseline is for a really dumb technique that just looks at word pair frequency, or maybe frequency with synonyms thrown in?
Okay, so backing up here, Michael Littman gave this as an assignment to his class in a course he taught. And he divided the class up into groups of 3, 4, 5 people. And I think there was 14 or 15 groups altogether. And they tried all sorts of algorithms, a huge spectrum of algorithms. And the kinds of scores they were seeing were, well, first of all, random chance, random guessing gives you 20% correct, because there's 5 choices. They were seeing scores around 30%. The very best score was something like 32%. So the vector space model right away gives you a big gain over sort of naive approaches. And again, you can see if you go to latent relational analysis, you get even more of a gain. You go up from 47% with Alta Vista to 56% with a corpus that's 1/10 of the size of Alta Vista.
So the VSM, the vector space models here, what exactly are you doing? Are you still doing the Thesaurus expansion? Or is the vector space model exactly what you did in the earlier work?
It's exactly what I did in the earlier work with Michael Littman. I just replicated it here for comparison.
Okay, so it's the 60 fixed phrases.
64, yeah.
Right. So if you do an SVD on that, do you know what you get? I mean,
it doesn't help because so there's 64 joining patterns. You get 128 elements in your vector. It's just not big enough. I tried using a singular value decomposition, and it decreases the performance no matter what you do. There just isn't enough data for the singular value decomposition to work with.
There are a lot of parameters there. I know, picking 4,000 things, the 3 best things, I know, picking things that have actually a cosine larger than the original pair. How did you make those? Because I don't see a development. I don't see a split here, development test.
I didn't really play with those parameters.
On the test set?
No, I just picked them arbitrarily. You see, most of them are, I have to consider the number of patterns. I took the top 4,000. Basically, I took as many as I could. If I have millions of patterns, and there's no way I could build a matrix with 1,000,000 columns. So I had to cut it somewhere. So basically, I took as much as I could and keep the computation within bounds. Because I didn't mention this, but this took 9 days, I think, to do all of the SAT questions. It was running flat out for 9 days. So I had to cut things somewhere. And basically, all of those parameters were cut rather arbitrarily just to keep down computation. I didn't try tuning them. My intuition is if I bump up any of them higher, the score will go up. But I just can't afford to because it's already taking a long time to run. I didn't mention this also, but I'm using a Beowulf cluster with 16 CPUs to do the bulk of the computation. And so flat out for 9 days on a Beowulf cluster with 16 CPUs. So it's... Yeah, most of the time is spent just searching for all of the phrases that contain the words.
But then you can actually plot a curve for, I know, less than 4,000.
I could.
Taking...
I could, but just plotting that curve would take a long time.
How that curve looks like.
Yes. Those are good questions, and I should do that someday. But just getting the data points I need for that curve is probably going to take 2 months of running.
But you already have it.
No, I have one point.
You never saved which frequencies come from which pattern?
I have to recalculate basically everything because.
I don't see why you have a pattern frequency matrix. You can cut back the number of patterns and redo the other.
I can reuse some of it, but a lot of it's going to change. But I should do that. You're right. Yes?
Are there any estimates out there as to how much text a college-bound kid is seeing?
Ask the person 2 feet.
Probably not a terabyte.
Or if you gave him 9 days to work on the analogy section. And a large corpus.
I guess the performance would go down. Start second guessing themselves.
A few megabytes.
There are some practical limitations to the algorithm. So the next batch of experiments are noun-modifier relations. I have 600 noun-modifier pairs that were manually labeled into 30 classes. And here's some examples. I won't show you all 30 classes, but flu virus, the relationship there is cause. The virus causes the flu. Hometown, the relationship is location. Printer tray, the tray is a part of the printer. Weather report, the topic of the report is the weather. These 30 classes have been grouped into 5 groups. Causal relationships, temporal relationships, spatial relations, participatory relations involving usually an agent and an object, or subject-object sort of things, and qualitative relations. So I have 2 experiments with these, one using the 30 classes, the fine-grained classes, and one using the 5 classes. And as I described earlier, this is I use a single nearest neighbor algorithm. So this is now supervised learning. The previous SAT stuff was unsupervised, but now I'm putting a little supervised algorithm wrapper around it. And the wrapper is a very simple nearest neighbor algorithm, and the distance measure comes from the latent relational analysis. So I'm doing leave one out cross-validation. So I split the data 600 times with 1 testing case and 599 training cases. And I look at the precision, recall, and F measure, macro averaged. Here's the result with 30 classes. Again, I'm comparing 3 different algorithms, or 2 algorithms. The vector space model, I'm looking at 2 different sized corpora, the Alta Vista model and the Waterloo multi-text system. The bottom line here, I guess, is the F measure, and you can see it's gone up 10% from the vector space model to the latent relational analysis model. Actually 15% if you match the corpus sizes. But 36% is still not as high as I would like it to be. And here are the results for the 5-class problem. And now latent relational analysis is up to almost 55% on the F measure. There's still a lot of room for improvement here, but it's definitely doing something. The algorithm is getting somewhere, and I think it's a promising result. So the experiments show that latent relational analysis works better than the vector space model. Is it working well enough for practical applications? Maybe for some practical applications, but for most, I would guess we need to do a bit of improvement. For one thing, the 9-day running time is probably a bit long. But I think that problem will go away as hardware gets better. And the Alta Vista, the 17 days for Alta Vista, that's not entirely fair, because when we did the Alta Vista experiments, we used a 5-second delay between all the queries so as not to overload Alta Vista. But now that with the Waterloo multi-text system, that's in-house, and we can issue the queries as fast as we want, and we can issue a couple of queries a second. So future work, I'd like to improve the accuracy, and once I've improved the accuracy, then I want to show that this really is useful for the various applications I talked about, like machine translation, information retrieval, show that there's some real benefit to it. Another thing I'd like to look at is work that's been done before with analogies such as Gentner's structure mapping engine. I think that there's some room for some synergy, some hybrid between what I'm doing and what Gentner's done. And another thing I'd like to play with is, instead of having a fixed list of relations, for the noun modifier pairs there was a fixed list of 30 relations. I'd like to try to extract from the corpus what the relationship is between the word pairs. Because there's many cases of kind of idiosyncratic relationships that, well, mason stone, what's the relationship there? The stone is a material that the mason builds with. do you really want to have a classification scheme that's so detailed that it really captures the relationship between mason and stone? It makes more sense, I think, to kind of build your classification scheme on the fly as you encounter cases. And I'm hoping I'll be able to look in the corpus and from the corpus extract a good name for the relationship between the given word pair. So last slide. What have I done? I've shown a new algorithm, Latent Relational Analysis, that gives human-level performance on SAT word analogies. And it extends the vector space model that I did earlier with Michael Littman in 3 directions. And I believe that there's lots of potential applications here. Basically, anything that's being done now with attributional similarity, which is an awful lot. All today's search engines basically are measuring attributional similarity. That's how they sort their results. Anything that's done now with attributional similarity, I think, can benefit from having relational similarity as well. So that's it.
Can you elaborate on that very last sentence? Right. So it's just not obvious to me how any given search could benefit. Just name a search and tell me how.
Okay. I have some examples in the tech report that this is based on. For each, I list maybe 9 applications, and I think for each one I give some examples of how relational similarity could help. Very often, so in information retrieval, how would you use relational similarity? Well, suppose you're searching for flu virus, and you type in flu virus as a query. You'll get any page, any web page that mentions both the word flu and the word virus. But perhaps all you're interested in is web pages that talk about the causal relationship between virus and flu. And so if you could somehow further qualify your query by saying, I want pages that have the word flu in them and the word virus in them, but furthermore, I only want pages that talk about the causal relationship between flu and virus. You could make your search much more precise. So how would you do that? Well, if you had a good measure of relational similarity, you'd be able to classify the relationships, and you'd be able to go through your documents as you're indexing them and figure out the relationships between the words and add that as sort of metadata to your index. And then people would be able to use that metadata when they're searching. So that's one example, but I think there's others, and I give some more in the tech report.
For the noun-modifier pairs experiments, have you tried any other classification than cosine? Because, I know, in our word sense disambiguation experiment, we tried a lot of things, right, on the vectors. And cosine was by far the worst. So naive-based, decision lists, TBL, everything beat it just applying cosine. So, I know, I'm just curious if you tried something else.
Yes, since this is supervised learning, instead of cosine, I could just take these vectors and feed them into any supervised learning algorithm. In fact, I did this. I took the Weka toolbox and fed these vectors in and tried a whole bunch of different learning algorithms. Single nearest neighbor was the second best to all the ones I tried. The very best was a neural network, but it took a long time to train the neural network. So naive Bayes, support vector machines, they were all substantially worse than single nearest neighbor. It's important that you calculate the cosine on the right matrix. So the part of the processing of the matrix is to take the logs of the frequencies and calculate the entropy of the columns and apply the singular value decomposition. Once you've done that, the cosine, it seems, does quite well. But if you apply the cosine to the raw frequency data, it doesn't work very well at all. So it's really important to fiddle around with the processing of the matrix. And again, I just borrowed all of the techniques that have been used in the past in latent semantic analysis and use them verbatim, basically. The entropy calculation, taking the logs, applying the singular value decomposition, truncating it at 300 dimensions, all of that I just borrowed exactly with no changes from the latent semantic analysis literature.
I could well imagine that that the 64 join words work quite nicely then for the noun-modifier relations, because oftentimes the noun-modifier relations can be paraphrased by exacting prepositions. So I was wondering, for the analogy questions, are some...
Well, these are using those. The two VSM columns here are using those original 64 terms, and it's still not working as well as dynamically creating the joining term.
But are there some word analogy questions that are better answered? There are different types of analogy questions. Some are noun-noun, where the stem is both noun-noun, and some are noun adjectives, some are noun verbs. Are there some types that are better answered than others?
That's a good question. I didn't look at that. I did an experiment where I separated the SAT questions according to their pattern, like noun, 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 verb, adjective, noun, and tried to see if different joining terms would be appropriate for the different words, and there didn't seem to be much benefit to that.
I mean, in particular, the fact that you take a window of 5 might influence what types of questions you can. Like, a window of 5 would probably more easily answer a noun adjective or even a noun verb than maybe a noun noun.
One thing I didn't mention is that I'm doing a kind of stemming on the words. So given court and volume, I don't require an exact match with court and volume. I allow different suffixes. So some of that stemming will switch between part of speech. So, court volume doesn't work very well, but for some of the words, one stem would give you a noun, another stem would give you an adjective or even a verb. So I'm kind of blending across parts of speech, and that may be costing me something because I'm confusing different parts of speech. It may be hurting the performance a bit, but on the other hand, it improves the performance because I get more data. By being more generous about how I match these patterns, I get more data, and that seems to offset the cost of mixing up parts of speech.
For the first experiment, have you tried to do clustering and see what kind of just hierarchical clustering and see if the clusters make sense? Or is just basically you have a relationship and then you find, right? It could work beautifully, finding the closest to it, but if clustering doesn't give you anything, it's kind of hard to apply to anything else, basically.
I disagree. Okay, there's two questions. Did I try clustering? And the other is, do I need clustering? I haven't tried clustering, but just subjectively looking at the SAT questions, probably the most common kind of SAT question involves a type of relation, like lion is a type of cat. But many of the SAT questions involve idiosyncratic relationships that only appear in that one SAT question and don't appear in any of the other SAT questions, like Mason Stone. I believe that's the only SAT question that involves that particular relation of X is a craftsman who works with material Y. I think that relation is unique to that SAT question. Water is to riverbed as traffic is to street. The relation there intuitively is something like flows or maybe carries. A riverbed carries water. That's completely unique to that particular SAT question. None of the other SAT questions involve that particular relationship. What I expect you'd see is some sort of zip slaw thing, where there's a few high-frequency relationships, and then you get this sort of infinite tail of quite rare relationships. And any kind of fixed schema, like the 30 classes that I use for the noun-modifier relationship, is going to just capture the top end of that Zipf's-Law curve. Now, do you need clustering for applications? I think for some applications it helps to have fixed classes, and that's why I looked at the fixed set of 30 classes for noun-modifier relations. But for others, what you really want is some sort of measure, the numerical measure that's on a continuous scale. Just like with documents, sometimes you want to cluster your documents and say all of these are in cluster A, all of these are in cluster B. Other times you want to say take this sample document and show me the ones that are related to it in ranked order. And search engines, for example, are not doing clustering. They're just ranking by a similarity measure.
I completely agree with that. Probably I didn't phrase my question right. Is what happens if you put all those things together? Will you get, for mason stone, will you still get, what was the carpenter wood? Or would you get, traffic and street? That's my question.
That's a good question, and we actually did that. Michael Littman and I did that experiment in our earlier paper with the vector space model. So what we did is we took the 374 SAT questions and took all of the correct answers and made a big list of 374 choices. And so for each question, each stem pair, we knew that somewhere in that list of 374 correct answers was a correct answer for this stem pair. And so we expanded from having 5 choices to having 374 choices. And we got some interesting results. We looked at the top 10 of the 374 answers, and I think 20 to 30% of the time the correct answer was somewhere in the top 10. So it's doing far beyond random chance. This 10 over 374 is, I forget, 0.2% or something. So it's doing much better than chance, but still it doesn't, the single top choice is only rarely the perfect answer. But actually there's one example that's interesting. The stem pair was tourniquet bleeding. And the top choice was antidote poison, which I thought was a really good match, but it wasn't the intended match. The intended match was splint movement. Actually, kind of like antidote poison better than the top match. But that seemed like a creative solution to me. That's just subjectively speaking, no?
Is there an understanding as to what this test is testing? Is it testing vocabulary size? Is it testing how much you've read? Or is it testing analytical, mathematical type skills?
Well, that kind of criticism underlies why they dropped it.
Yes.
Because they don't know what it is?
That question, and also there's a bunch of ETS internal tech reports where there are systematic biases where the test discriminates against ethnic groups or favors ethnic groups depending on the kind of question you give.
And I don't think the results correlate with analytical skill results.
But it is testing, the real question is it testing how much you've read?
Yeah.
Well, I think the intent is it's classified, I think, as a reasoning or analysis test, even though you're right, it might be testing vocabulary more than anything.
The comments I heard, I did some searching on the web for a discussion about why they dropped analogy questions from the SAT, and there seem to be 2 general answers. Well, the actual course of events is in California, the University of California, the president of the university said that he thought the analogy questions were dumb, and he was going to boycott the SAT unless they dropped them, and basically that's why they dropped them, because of the size of that single university. But the reasons that he gave, reading between the lines, one is there are all these SAT preparation classes that students can go to, so they'll do well on the SAT. And apparently they found that while these SAT preparation classes do help for a lot of the SAT, they don't seem to help for the analogy questions. They would drill these students with these analogy questions to try and make sure they get a better score on the SAT, and no amount of drilling seemed to help. The students,
like the perfect test in that case. They should have dropped everything else.
No, that's the objection. You see, the Scholastic Aptitude Test is supposedly a measure of how much education you had or something, rather than a measure of IQ. In fact, it was originally called the Scholastic Aptitude Test, but that's not its name anymore. You're supposed to call it just SAT, and it doesn't stand for anything anymore because they don't want it to be an aptitude test. It's not supposed to be an IQ test. It's supposed to be some measure of your level of education.
Yeah, but being able to cram at the last minute of these schools kind of...
Well, but that's probably a very relevant skill to doing well in college, right?
But you're talking about the economic power, then the cramming courses probably have a lot of literature, right?
Well, technically, the College Board runs the tests, and ETS just puts them together for them. But so ETS is caught in this political bind where if the College Board takes heat, they make ETS change it. Yeah.
But I think there's a kind of something behind your question. I think what you're getting at maybe is, why do we care about the SAT test? Why do we care about analogy questions?
Or so what would be the method to building a program to do this? The question is, would it help to just expose it to more text, or is it helpful to have some deep art, AI or something?
Is there anything to deep AI beyond more text?
Well, all right.
I mean, you are on the third floor, right?
Well, someone might say that there are people who are good at math, and there are people who are good at who've read a lot, and you would wonder which of these types of people are likely to do well in this.
So Michael Littman got me interested in this. He said, I'm trying to answer these SAT analogy questions, and I at first thought, that looks really hard. I don't think you have any chance at that. But I decided to try it, and started to get some interesting results. And then I started reading about analogies and metaphor, and I read a whole bunch of Lakoff's books and Gentner's books, and now I've become obsessed by analogy, and I've become convinced that it's the core of cognition, and so I'm really interested in the SAT test as a kind of a probe that exposes that kind of difficult to objectively evaluate aspect of cognition. So that's why I'm interested in it now.
So, sort of in that vein, I have an objection to the way you average these scores for the SAT stuff, just because you're supposed to not only pick something which bears a strong similarity to the answer, but it's the only one among the 5 that has that specific relationship, and it's distinguished by it. Using the same information as what you have, can you...
I don't think that's true. In fact, okay, I guess we really need to talk to someone who's an expert in educational testing, but it seems to me that part of the reason they have this as multiple choice, like another way of doing it would be to do it as true-false. They could say, here's an analogy. Is it a good one or a bad one? And you can just say true-false. But I think actually there would be a lot more noise in a true-false test, because you would look at it and you say, well, okay, I can see that analogy a little bit. Is it good enough? Would I call it a really good analogy, or is it a bad analogy? I think introspectively, analogies vary in degree and quality, and so what's going on inside our brain introspectively seems to be some kind of continuous level of degrees of similarity. And the SAT test, by being multiple choice with 5 choices like this, allows it to be a matter of degree, because all you're asked to do is pick the best one. You're not asked to draw a threshold and say, is it good enough to be called a true analogy, or does it fall below that threshold and you have to call it a false analogy? I think fundamentally in our brain it's a continuous thing, and to say one of these analogies is absolutely true and the other 4 are false I just don't believe that.
No, more that this one stands out. So the relationship between the stem is, you might observe it in 2 of the possible responses, and some other relationship is only observed in 1, and so that one's the better one.
I don't agree with what you're saying. Having looked at all these SAT questions, there are some where it's really hard to say. There's a second choice that looks really good, sometimes better than the first choice. So I don't agree. Now, maybe I'm not an expert in educational testing, and maybe they'll tell you, maybe they say, yes, there's one that's the right answer and the other are false, but I don't believe that myself.
Well, presumably that would be their goal in designing the test, so they don't have people arguing with them.
You can't argue with them. You're good at scoring.
It's a question about stemming and also about what you said right now. If you had in the first case you presented, for example, photographer camera, right, and there was no carpenter wood, then probably that would have been the
But
best.
that was photograph, actually. So that one was clearly out just as far as speech comes.
Yeah, but
He's using derivational morphology.
No, because this one's photograph camera.
But
as
if
opposed to
it were photographer, right?
Right.
And the first argument is that I don't think, I'm just saying you're right, that probably I would have picked that if it was photographer and no carpenter would, thinking that it's analog. So pairing, it's probably not good enough, so you have to pick the best.
So why would you pick photographer camera over soldier gun then?
Well, so the thing is, the thing is that these things, this is why, analogy is sort of like a much tighter relationship than association, right? So, there are these different levels of analogy. Yeah, soldiers and gun have this sort of, occupational relationship, but same with photographer and camera and carpenter and wood and teacher and chalk.
Yeah, but you build something with
You
camera, you don't build anything
much
with
more
camera.
specific one, which is, works with, or writes with, or fires.
Well, for photographer camera, if you gave me mason, I would say chisel or hammer, because the camera is a tool, and so we would look at what tool the mason has.
True, but my question was actually, I just wanted to make the point of pairing that could be bad. Right? I'm not a native English speaker or something. But since you were actually doing the stemming, weren't you introducing a lot of noise though to these things? Because suddenly, if photographer and photographs just stem to the same root.
So I tried it with and without stemming, and stemming helps. Now, I agree intuitively stemming has bad things to it. Empirically, it seems to help in the end. But I can see reasons why it would hurt and reasons why it would help, and I guess the net balance is more on the helping side. Maybe the ideal algorithm would do something more sophisticated.
Discount the derivationally related forms or something.
Yeah.
I had a similar, I wonder, how if you have a pattern and you swap the terms around, that also feels unintuitive to me, because the patterns are nice because they're data driven. So, of the 4,000 patterns you get, you found them in the text, but you found them with X pattern Y. You didn't find them Y pattern X, and it may be a completely different relationship if it were in the order Y pattern X. And so I'm not quite, it's almost counterintuitive that, swapping would help you.
The swapping idea is essentially you could take any SAT question here and swap all of the words. So instead of mason, stone, teacher, chalk, this could be stone, mason, chalk, teacher, wood, carpenter. And the same answer would be right, choice B, only it would be in the other order.
You have to swap both the stimulus and the response.
So in effect, by doubling the matrix, by swapping, by having the pairs in both order, in effect, I'm pretending I had a set of SAT questions that was twice the size of the original set, just generated by taking each SAT question and flipping all of the words. And that would give me exactly the matrix that I'm getting. So I'm just simulating more SAT questions than I really have.
But are you getting a new set of patterns for the flipped relations? I thought I
Yes,
understood.
probably there will be new patterns, but so that's you could say that's good because I've doubled the number of questions that I have, and I'm finding new patterns that I wasn't finding before because maybe there was a bias in the person who dreamed these questions up. Maybe they had a certain way. They always preferred putting one kind of word first and another kind of word second, and I'm removing that bias by doubling.
Question is, do you ever end up comparing the vector for mason stone to the vector for wood carpenter rather than carpenter?
No, they each have different rows in the matrix.
So
the algorithm is sensitive to the order of the words.
Yeah.
Thank you.